Okay, good. So the topic today is what is known as plasma. So we are going to talk about, until now we have been talking about a single heavy nucleus or proton at high energy, which has its color field. We have been thinking about how a small dilute probe scatters off such a color field. And then yesterday we were just looking at the properties of this color field without actually calculating a cross-section for any kind of interaction, but just looking at the fields in different gauges. So part of as I said yesterday, part of the reason that we wanted to go to light-bound gauge was to enable us to do the calculation we're going to do today. Okay, so this is the plasma known as so this is the word Larry invented for the color fields Larry McLaren invented for the color fields of a heavy ion nucleus. So basically, we are following a calculation of 5 paper, which I always remember by KM. So there's actually 2 KMW papers that have been very important for me. The other one is and it's different K and different M and different W. The other one is Kowalski, Motika, Watt. But this one is Kovner, McLaren, and you can guess who the W is. Okay, so we're going to follow the calculation that was originally done in this paper. Okay, so what we want to do is that now, yesterday we had 1 heavy ion, now we want to have 2 heavy ions. So we're going to say that our current is a sum of 2 currents. Okay, so we have a delta mu plus. There's a current going in the plus direction. I will call this a rho 1 of x per. And this current lives on the light cone. This is the current we had yesterday. And then we're going to add another current going in the minus direction, which it's a different nucleus. It has its own charge density. And it is going in the other direction. So it's kind of Lorentz contracted in the other direction. Good. So let's draw a picture of space-time. So now I'm splitting space-time into regions. This is the x minus axis, x minus axis, x plus axis. This is time. This is z. So I now have 2 heavy ions going on at speed of light in the opposite directions on the light. I will call this region of space-time number 4. So this is kind of, if you're sitting here, kind of sitting, you're looking at a heavy ion approaching you from that direction, not yet reaching you. You're looking at another heavy ion. See, it's coming at you from over there. You can't see it, of course, because it's coming at the speed of light. But you might guess that it's coming. But here there's a vacuum. So we are, and to some extent, this is a choice of gauge, but somehow it's kind of the natural thing for this physical problem. We are working in a gauge where the gauge field here is 0. Nothing has happened. Okay. So then when we go to this region, this I think is my region 1. This is my region 1. So we just sit here and we go. If we don't move, we're just going up forward in time. So we go to this region. So what happens is that the nucleus going in the positive direction now has hit us. Okay. So now we're sitting in a region where the one going in the positive direction already went by, but the other one is still coming from there. So we've only seen one of the nuclei. Yes.
Just to clarify, is this an effective description of 2 heavy ion?
Yes. Yes. This is what we want to do. We want to do the collision of 2 heavy ions.
Right. It's just the only place where I've actually come across the concept of a plasma was in a Larry McLaren lecture as a successive state to the color glass condensate. So I'm just a bit curious as to how one gets from the color glass condensate to a glass rod, because the CGC prototypically involves a interaction between a lepton and a hadron.
Well, the CGC is a theory about how you describe the hadron of the nucleus, right? And then you can use the CGC description of a hadron to calculate DIS. Here we're going to use the CGC description of a nucleus to describe a heavy ion collision. So the plasma is what you get when you have two CGCs colliding and hitting each other. And this is and how you get from the CGC to the plasma. This is what I'll try to explain today. Good. So we're sitting now. If we're sitting here, one nucleus passed by, the other one is still coming. We haven't seen the other one. So as we remember from yesterday, now we're in light cone gauge. In this region of space-time, we have a transverse field, pure gauge field. This is a gauge transform of vacuum. So there's no energy density here. And the other nucleus is still coming towards us. We haven't seen it. The first nucleus already went by, and we're kind of sitting in the vacuum that is left behind it. So there's no energy density. But as we remember yesterday, in light cone gauge, there is a non-zero gauge field. This transverse pure gauge field, which you can write as a gauge transformation of the vacuum. So in this region, we're sitting in the pure gauge field left behind by the nucleus that already passed us on the way over there. On the other hand, in this region, I think I call 2, this is the other situation. And now here, it's the nucleus going that way that already passed by, and the other one is still coming. So if we're sitting here, the nucleus coming from over there already passed us, and it left behind it a light cone gauge field, 2, right, which is completely independent. It doesn't somehow at this point, these nuclei don't yet know anything. Don't yet know anything about each other. Okay. So, and now the problem that we face in a heavy ion collision is what is the gauge field here? This is the region where both of the nuclei have passed, and here we are sitting in the system that is going to become a quark gluon plasma. And this is the topic that we want to understand. How do we understand what it looks like to be in this part of space-time? And now we're doing completely classical chromodynamics. We have currents, we solve equations of motion, classical equations of motion for the Young-Inglis fields, and we want to figure out what do the classical equations of motion for the color fields tell us about what it looks like to live here. Okay. Good. And just to recall, I will write down the expression. So this AI 1 or 2 is an I over G. I'm not sure I'm fully consistent, but 1 or 2. So both of them have their own Wilson lines. The dagger 1 or 2. So both the light cone gauge fields of both nuclei have their own Wilson lines, and the Wilson lines 1, 2 are now I'm kind of dropping the, well, I can write it as a path order, but I'm kind of write the path order in here. I rho 1, 2 over radiant squared. I'm kind of being a little bit loose with the longitudinal direction here, which we went through pages to describe yesterday, but let me write this one properly. Nevertheless. So dx plus or minus rho 1 over radiant squared, and there's a g, and rho 1 or 2 x per and y plus x plus or minus. Okay, so these are the Wilson lines. One of the Wilson lines is going in the plus direction, the other one in the minus direction for the nucleus 1 or 2.
Yeah. How do you justify having two separate gauge transformations?
Well, at this point, I haven't gauge transformed anything, right? At this point,
Okay.
at this point, somehow yesterday it was kind of, we did the gauge transformation because we first found a solution to the equation of motion in some gauge, but then we decided this is not the gauge we want to use, so we made a gauge transformation to another gauge. Of course, we could have yesterday just directly figured out the solution to the equation of motion in the light cone gauge with only transverse components. And so we would not have needed to do a gauge transformation. We could have just, I have a solution in this gauge. That's fine. I live with this solution. And now, so far, these are now both A plus and A minus are 0, right? So this is this kind of a configuration is so far a perfectly good solution of the equations of motion everywhere. Okay, it's an equation of motion that satisfies, just happens to satisfy both light cone gauge conditions. Both A plus and A minus are both 0. So this is so far a perfectly good solution. We just obtained it by solving this problem in one gauge and gauge transforming, solving this problem in another gauge and gauge transforming, but the result of after these gauge transformations is a perfectly good solution of the equation of motion.
At least in the regions that you know specified.
At least so far. Okay, at least so far. Okay. So then inside this region 3, you remember our currents just live on the light cone. So inside this region 3, there is no color charge. Okay. So inside this region 3, our equation of motion is just going to be that the covariant derivative of the field strength tensor is 0. There are no sources here, and that's kind of that's something that we want to do because it's part of kind of the effective theory description idea. What we want to achieve here is that we want to get rid of the sources. We could of course do classical Yang-Mills and Wong's equations to solve classical equations of motion for classical charge particles. Conceptually, that would be perfectly fine, and there are actually attempts to do that numerically. But that's kind of we would not be using the full power of the effective theory approach, where the effective theory approach is that here the physics we are interested in is the classical field, and once we get into the physics of the quark gluon plasma here, we don't want to have these charges around anymore. They're gone. We want to be able to, we want to solve, that's the reason we make this strict scale separation. Charges are here, fields are here, and so that we can eventually just, once we get far enough, we can forget about the charges and just study this equation. Okay.
So like math, you also mid rapidity.
I'm at mid rapidity, yes. So now I'm interested at mid rapidity. Okay.
Yeah. So you're not thinking about the actual plasma as a charge, like a charge at all. It's the what Jamie is 0. Right?
Yeah. So these charges, they're kind of they are not what's going to be the plasma. These charges are the valence quarks. When the nuclei pass, the valence quarks from the receding nuclei are going to go their way, and they're going to leave behind them some stuff that is going to become the plasma.
But are you treating that stuff as not having any?
Yeah, and that stuff that stuff here only has color fields. It does not have color charges. Of course, it has color fields are gluons, and gluons have color charge. So there is color, but all of the color is in the classical field, this region, and there's no color in this. There's no color in classical color charges. All of the color is in the color fields. So there is color, there is matter, there's energy density, but all that is, I want all of it to be in the classical field, not in any classical charges. So, so then, so of course, but it's the charges that somehow give rise to the matter that is here. So somehow we need to work with the charges for a little bit before we can forget them and just concentrate on this equation, right? So what the charges give you is an initial condition at tau equals 0. Okay, so tau is the proper time. Let me draw another here. Here I'm using proper time, and I will be doing this calculation in proper time and space-time rapidity coordinates. So proper time is defined as tau squared equals 2x plus x minus. Okay, and space-time rapidity eta is defined as, I think it's 1/2 log of x plus over x minus. I hope I'm gonna need this a little bit less. I hope the factor is right.
Tau squared is x0 squared minus x3 squared.
Yes.
How is this?
That's the way it's called. It is a so
It's
it-
proper
the-
time for this is the distance where one of these hyperbola
No.
goes through.
So the first, why is it a time? First of all, why is it some kind of a time-like variable? Easiest to if you sit at mid rapidity, if you sit at z equals 0 in the center, then this is just the time, right? So this means that if you are going exactly on, if you are just sitting here and not moving, this is the time. Then this expression is boost invariant in the z under boosts in the z direction. So this is it is also the time variable that you get if you boost to a system that is moving at a constant velocity in the z direction. Okay, so let's draw these. Let's draw these a little bit in our space-time. In our space-time diagram, here's x plus, here's x minus. A constant, so a constant tau surface is, you can see that it's x plus times x minus is a constant. So constant tau surface is a hyperbola. These are tau equals constant surfaces, are hyperbolae in this coordinate system. What is a constant eta surface? Constant eta surface is x plus divided by x minus is constant, so x plus is proportional to x minus, so it's a straight line. So a constant eta surface is a straight line in this diagram. Okay. You can hopefully believe me, and you can check if you want, that if you do a boost in the z direction, if you boost in the z direction, tau does not change, and eta gets a linear. In a boost in the z direction, eta just gets shifted by a constant. Right? So a boost is going from such a surface to such a surface. Tau doesn't change. Eta gets shifted by a constant. So boosting takes you from eta to eta plus the rapidity of the boost. Okay. Good. So this is our coordinate system, space-time rapidity. So we're going to need. So this is why I say I need an initial condition at tau equals 0. So tau equals 0 is the. So tau equals 0 covers both of these light box, right? Okay. So tau equals 0. I need an initial condition for this region 3, and I need it at the surface tau equals 0. Okay. Then one more thing. We are dealing with collision energy being infinite. We're working in the infinite collision energy limit. Okay, so I will postulate that if the collision energy is infinite and your infinite somehow boosting, and infinite plus something is all still infinite, right? So if my collision energy is infinite and I boost to a different frame, I should be seeing exactly the same physics. This is an approximation. In some sense, this is a good approximation, but I'm actually going to be using it in a sense that is less good approximation. We'll come back to this tomorrow. Okay, but right now I'm working in the simplest thing, which is that I'm just saying that this is a slightly dodgy. Okay, and we'll come back to this tomorrow. I'm just saying that I will assume, based on the fact that the collision energy is infinite, that my fields at the level of the field configuration. This is the kind of the shaky thing, right? But I will now claim it that my fields, all the components of my gauge field are boost invariant. So this means that they, in this region 3, that they will only depend on proper time and transverse coordinates. So the boost invariant means that I will have field configurations which do not depend on the space-time rapidity. Okay, so they are functions of proper time and transverse coordinate only, not of space-time rapidity. Okay. And this is I'm making a very strong assumption here, which is overly strong, but we will come back to that tomorrow. Okay. So these are some aspects. Now, okay, so these are features that we know for the color field, and what we want is, of course, you can already see what we want to get is an initial condition for this gauge field in terms of these two gauge fields. These two gauge fields are kind of going to determine what our field in the future. They are going to give the initial condition on the line. Okay, so now the genius of this KMW paper was that there's a specific gauge where it is convenient to do this calculation. This is a gauge that had been studied by, I think, Machlin. I don't know, did you know Machlin?
Yeah.
I never met him, but I've seen the paper.
I know him, but I didn't know that.
I think he had been doing a lot of stuff in this. So we are going to make a gauge choice, which is a very peculiar gauge choice. Okay. We are going to make a gauge choice where the tau, the proper time component of our gauge field, is 0. Now, what is a proper time? Of course, here I have defined the coordinate system. If you have taken if you take a relativity, you will be able to take this coordinate system, calculate and it's a curved coordinate system, so you need to be a little bit more careful in differential geometry to know how to take derivatives and how to take components of vectors and so on. I will not go into this mathematics here. I will just state that if you do the Lorentz transformation properly to this kind of a coordinate system, the tau component of a vector will kind of be quite naturally x plus a minus plus x minus a plus and 1 over tau. Very weird gauge choice. but it's actually, it's kind of you wouldn't do this in a perturbative calculation. You wouldn't start calculating Feynman diagrams in such a gauge. But we're doing Feynman diagrams, we're solving classical equations of motion as an initial value problem.
And you still have freedom because you've already chosen the field to be 0 and A4. It's also kind of a gauge choice.
Well, let's say it's not obvious, but if I can find a solution in this gauge, it's not guaranteed that I will find a solution in such a gauge that satisfies both this and this. But if I do find a solution, then I'm fine, right? And so let's look at what this means in terms of our light cone gauges. So if we now go to x plus equals 0, okay, so I'm going to this surface here. My gauge choice means that A plus equals 0. So x plus equal, yeah, so x plus equals 0 is the gauge choice that sets on this surface. My gauge choice is that A plus equals 0. So here on this line, I will not have my A plus will be 0, and if I look at it, this is so I have to think that I'm doing this right. X plus equals 0 is the x plus equals 0 is the x plus is equals 0 is the that's where the current that is going left lives, right? So this is here. So here the current that is going left, this was the field of the current that is going left. It's kind of the one that lives after the current that is going left. And this was a field that we obtained by choosing a light cone gauge A minus equals, it was a gauge that this was something that we obtained by choosing a light cone gauge A minus equals 0 to get this. And then accidentally, our solution also had A plus equals 0. And this accidentally, it was kind of resulting from the fact that we argued that this there's no x minus dependence. We were when doing the gauge transformation, this current did not depend on its appropriate light cone time x minus. So this for this field, this was a gauge choice, and this was just an accidental property of the solution related to the fact that this current was not depending on its time variable, right? And likewise for the other surface, when x minus equals 0, this condition means that A minus equals 0. So here it is something that is this field is satisfying because of course these fields have, so both of these fields have plus and minus component 0, one by gauge choice, the other one by accident, the other one is just happens to be a solution of the equation. The other one is a gauge choice, but nevertheless, these are both satisfied by both of these fields in these regions. We have a solution that's the solution we have. You have a question? No. So now why is this a nice choice, gauge choice for this problem? Minus. So if we look at here, so now even in this forward light cone everywhere, our gauge choice is such that A plus is 0 here, right? And this is the region where the J minus current lives. This is the J minus current which is living on this light cone. And the J minus current interacts with the gauge field like this, right? But now we are in a gauge where this is 0 here, where the J minus current lives, right? And vice versa. Here we have a J plus current, which would like to interact with the A minus component, but our gauge choice is such that here A minus is 0. And it doesn't. So this means that, remember that the current needs to be covariantly conserved. So we have our E mu, J mu is 0 for covariant conservation of the current. This means that this is kind of trivially satisfied, right? Because somehow we don't, the commutator, the gauge field in this particular gauge, even if we have this current with two components, our gauge field does not color rotate the current. So we can do this calculation by just keeping the current like this. The current does not need to be gauge rotated. The gauge fields, our classical gauge fields will not be gauge rotating our currents. In either of these places where this could might happen. It is possible to do this calculation at least in some limit in a covariant gauge, and then you have this gauge rotations, and that is and you get the same result to the extent that you can do the calculation, but you cannot do the calculation to quite the same extent as in nonlinearity as you can here. Here I can already, since Matt was just talking about this morning, I'll make a little digression from what my original plan was, and I'll redraw the diagrams that was drawn. And the third one. Now, Matt was saying that Matt's calculation was calculating these 5 diagrams, shuffling around, and getting everything to be just a single, effectively part of vertex. Right. What we are doing here, when we are calculating the production of gluons here, calculating the gluon field here. So what we are doing is kind of a classical non-perturbative limit of, I mean, these diagrams are a perturbative limit. There's our perturbative limit of our calculation here. Actually, in principle, we're doing a classical calculation. This was a diagram calculation, but in fact, the perturbative weak coupling limit of the perturbative dilute limit of our calculation that we're doing here is actually reproduces precisely the result from that. That's because Matt was using Eikonol kinematics, actually the quantumness of this thing doesn't really matter in the Eikonol limit. It does, because in the Eikonol limit, you don't really care about the quantum nature of these particles, you just care about the fact that these have a color. So in Matt's calculation, he was calculating with quarks. But here, instead of quark, we have a color current. But since we're working in the Eikonol limit, the only thing that matters about the quarks is their color. And we can replace the quarks by color currents. Okay. So the gauge choice, Matt had to calculate all of these diagrams to get the right result. This is a particular gauge choice which eliminates all of this color precession. And this means that actually our gauge choice is a specific gauge that eliminates these diagrams. And we get the result in this gauge, we get the result from only this diagram.
Okay, so the non-quantum is a come from the quantum limit. It's not calculating at the 3 level.
Well, three level 2, but these are 3 level diagrams. Right? So of course, loop diagrams would be non-classical. But Matt was calculating these 3 level diagrams as in the Iconor approximation. In principle, tree-level diagrams are not always equivalent to classical fields, but in specific kinematical limits, a tree-level diagram, tree-level emission in the soft or Iconor limit is actually classical.
But you said you would not use this stage for the computation now.
Well, I wouldn't somehow start doing the calculation like Matt is doing and trying to use this sketch. What I will do is that I will kind of get the result, and from the result I will kind of see that I do get the same result that Matt would be getting in a different gauge using this. So you see that this gives you a new interpretation a little bit to the. This gives you a new interpretation a little bit to these diagrams. So the way you can read these diagrams, that, for example, take a look at this. Look at this diagram. The way you can think of this diagram is that here is my one color charge. You can think of this in such a way that this color charge creates a gluon field. The gluon field color rotates the other color charge, and because the other color charge was color rotated, it's going to emit the gluon. And this is the same for all of these diagrams that do not exist in the gauge we are using. These are diagrams where the color field of one guy color rotates the other charge, and then because your color charge was rotated, you need to emit something. But now we are working at a gauge where color charges are not color rotated by the field of the other guy, and therefore everything just comes from gluons interacting with gluons. So that was a kind of a side note to relate this to Matt's calculation. Okay, so we are working in this gauge, and now we go to the way. Oh, and this is is known as Fock-Schwinger gauge. Fock-Schwinger gauge,
Or at least a variant thereof. I mean, it's
or variant there. I don't know what the original
the original is covariant, yeah, with some origin.
So the other thing that is convenient is that this is a temporal gauge, and if you want to eventually solve this equation numerically on the lattice equation of motion, that the temporal gauge is what you want to use to solve equations of motion in gauge theory numerically. So it's also convenient from that point of view. It's already in a gauge that I can use to put this on a lattice and solve this equation on a lattice. So that's an additional convenience.
On the lattice, you do not even choose a gauge, but you gauge when they work with units.
That's if you do quantum, if you do the path integral.
This is the classical.
But this is a class. So of course it is if you solve a classical problem as an initial value problem, so you do time evolution forward starting from an initial condition, then you prefer to use a temporal gauge. You can still, everything else is gauge invariant. You still work with links, and we work with links and electric fields. You do the calculation gauge in a gauge invariant way otherwise, except that you have chosen this. Okay, so that is kind of a side remark that this is also a convenient thing if you want to do this numerically. Good. So I think it doesn't make sense for me to go through all of the algebra, but what I will tell you the way these guys solve this problem. Okay, and it's actually very somehow straightforward way. And what I need to tell you is that now, of course, we have a little bit more degrees of freedom. We chose this gauge, so we have a transverse components. We have this temporal component which we have chosen to be 0, and of course there are 4 components in the gauge field. Here we were able to find a solution where kind of by gauge choice one component is 0, and by accident or as a property of the solution that the other component just happens to be 0. But of course, this was just a property of the solution for the single nucleus problem. For the two nucleus problem, we don't necessarily expect to find a solution where the last remaining component would somehow miraculously be zero. So we have to allow for the possibility that it's not zero. Okay. So we will allow for the possibility of there being an for the possibility of there being an eta component, and somehow my conventions are to write a eta upstairs. It makes a little matters. It does matter a little bit. So there will be an eta component in the gauge field, which will be non-zero in the region 3. And the A eta component is basically the same thing except the minus here without the top. And note, if you want to do this calculation carefully, you have to note that a lower eta is minus tau squared a upper eta, because the metric in these coordinates is 1 minus tau squared. And so that gives a little bit different. So you need to be careful whether your index is up, eta index is up or down. It brings you a power, it brings you powers of tau. Okay, so we will work. So this is the remaining component, and we don't know yet what it is. So how do we determine what they are? We will just write an ansatz. Right, an ansatz. We first write an ansatz for the transverse components. So the AI of the field, AI, the gauge transverse components of the gauge field, is going to be first of all, it's going to be in the region 1, we are x minus greater than 0, but x plus is less than 0. So theta of minus x plus. And here we know the solution. This is solution number 1. Then there's the other region where x minus, so theta function minus x minus, which means that x minus is negative. So we are below this axis in this region, and x plus is positive. So we are in this quadrant. And here we know our region, know our solution number 2. And then we will just write an ansatz that in our ansatz that there is some unknown, so far unknown field in the region 3, and x plus and x minus are both positive, right? And then it's easier for me to write like this. So I will, I only have what, so I have the realized remaining component is a theta. I will just express a plus and a minus in terms of a. Okay, and inverting this transformation, the result is that I will have an a plus, a minus, which are plus minus theta of x plus, theta of x minus. So these exist only in the region 3, and then x plus minus a. Good. And so here is my, so this is just kind of doing the Lorentz transformation, expressing plus minus components in terms of the eta component with the assumption that the tau component of the vector is 0. So this we can, if you want to go through this exercise, we can go potentially in the cut session in the afternoon. But for now, I hope that you will just believe me that playing around with this is what you get. Okay. And now I somehow wrote the arguments explicitly that these are now going to be, we are using our boost invariance assumption that these are going to be depend on how an expert. Right. So here's an ansatz, and these are the unknowns, and what we want to get is the initial condition for these in for the initial condition for these functions at tau equals 0, right? So that how do we proceed? I think I will not go through exactly every step of the. I will not go through every step of the calculation. I will just try to explain what we do. So we take our ansatz. So we take our ansatz and we plug it into the equation of motion. Right. So what kind of things does the equation of motion? And on the right hand side of the equation of motion, we have two currents, the plus and the minus current, which correspond to these two guys. In our ansatz, we have these fields, which we know how these fields are related to the current. So this A1 field is related to the plus current. So there's a relation somehow. Without the other guy, this is already in itself satisfies the equation of motion. So we kind of just plugging this ansatz into here, the plus current is cancelled by the term coming from here, right? And the minus current is cancelled by the term coming from here. In this, we are looking for the initial condition at tau equals 0. So we're just looking at the terms at tau equals 0. There are lots of singularities. Our current is a delta. Our currents are delta functions of the light. Right? Here we have theta functions, and we plug this into this equation. So calculating f mu nu is first of all a derivative of these. So when I'm taking derivatives with respect to plus or minus coordinates, I will get a delta function from the derivative of the theta function. Then in the equation of motion, I have a second derivative here, which differentiates again with the other. So the most leading singular terms will be things where the derivatives in the equation of motion act on both this and this. And so I will have this acting on this and this, acting on this and this, acting on this and this. There are some minus signs. Then there are things that then there are contributions where there are minus signs. Actually, the first equation is you don't even need to know about the currents. You just differentiate. You take the derivative, take the contribution where there's two delta functions, x plus and x minus. Delta function of x plus, delta function of x minus. So I plug all these things, and the ansatz into the equation. I look for the most singular terms. So if I first look at the coefficient of the delta function, which comes from both derivatives acting on the theta functions, I very easily see that, and the coefficient of this term has to cancel because I have to satisfy the equation of motion completely. So this leads to the following initial condition that A transfers 3 at tau equals 0 is just AI1 plus AI2. That's actually, you don't even need there. This is the simplest one. You just look at the most. It's from most divergent contributions. Then, so this is one initial condition. Then there's another initial condition for which you have to look at terms with a delta x plus and a theta x minus, and a delta x plus and a theta minus x minus. So these are terms where one of the derivatives acts on a theta function, while the other one acts here on the fields. And that's where you have to use the equation of motion. You know that these are related to the currents. The current also has delta functions of x plus and x minus. So this kind of term with one delta function, either x plus or x minus. The current has them. You get them from differentiating these differentiating one of these theta functions and then the other derivative operating inside on the gauge fields. Then there are the commutator terms, but those also you have to somehow make sure that everything is somehow carefully done. But those terms essentially vanish using the fact that you now know this, and you know that these two fields satisfy the equation of motion that gives these fields in terms of the currents. So there's a couple of bits and pieces that you need to put together. And the end result of this calculation is, I will skip the algebra, is that in order for the coefficients of these terms to vanish, you will need the A eta to be I G over 2 and a commutator of AI1, AI2. Yeah. Good. And now we're set. So this is the initial condition. Now, so this is at equals 0, and then these are the initial conditions. Now we have our equation of motion. We plug these fields into our equation of motion and we solve, and that's then we have the field here. Solving this equation of motion you can do analytically only in some linearized approximation, which enables you to understand a lot of stuff. But you can also do it fully numerically. So this is just putting this on the lattice and then solving it as a numerical equation. And this somehow set up. You go from the currents, which you can relate to Wilson lines, and the Wilson lines are things that you can make different higher point operators out of the Wilson lines. You can measure these Wilson line operators give you cross sections for deep inelastic scattering, proton nuclear quark nucleus scattering. So there are different processes, dilute dense processes, where you can measure these Wilson lines. On the other hand, you can take the same Wilson lines, plug them in here, calculate the pure gauge fields, put the pure gauge fields in these initial conditions, and then plug them into this equation and solve this equation. And this is a widely used procedure in heavy ion collisions. There's a whole industry. For example, I think that maybe the most known is this IP plasma. If you follow heavy ion phenomenology, you might have seen this IP plasma. It's a code which does precisely this. There's a specific model for what these Wilson lines are that is kind of related to DIS data. But what IP plasma really is the classical Yang-Mills equation, solver for the classical Yang-Mills equations, starting from this model for the DIS fitted model for the Wilson lines that takes these initial conditions, plugs them in here, and solves the equation of motion. So I think now maybe would be a good time to take a 5-minute break, unless you have questions first. 5 or 10 minutes. IP is impact parameter dependent plasma. It comes from a marriage of what is known as the impact parameter IPSat model, which is a parameterization for DIS data, which is impact parameter dependent saturation model, which is originally the Kowalski-Thieme model. Kowalski-Thieme model, which was later renamed. That's the other KMW, Kowalski-Motyka-Watt. Kowalski-Motyka-Watt, who called this model the IPSat model. They fit DIS data, vector data, total DIS data, and then somehow taking the Wilson lines from the IPSat model and plugging them into these equations is the IP Glasma code by Björn Schenke and company. And that is widely used. And then, of course, depending on, I mean, there are different bells and whistles, but different kinds of physics ingredients that you can put into the Wilson lines, and then into the different kinds of the physics ingredients that you can put into the Wilson line distributions, and then you run them through this machinery, and you initialize hydrodynamics, and then somehow it's a relatively successful model that is used in heavy ion phenomenology based on these equations. Good.
Sorry. And the lattice you use for this, presumably not adapted to this coordinates somehow.
So if you IP Glasma, so when you do these boost invariant simulations, you explicitly have boost invariance at the level of, so you dimensionally reduce. So what you will end up having is a 2D Yang-Mills plus adjoint scalar. Because you dimensionally reduce to these boost invariant coordinates, the A eta becomes if you want to maintain boost invariance, you're not allowed to make eta dependent gauge transformation that would break boost invariance. So this means that you dimensionally reduce, the A eta becomes an adjoint representation scalar field. The transverse components are just transverse gauge fields. So what you are simulating is a two-dimensional Yang-Mills, two spatial dimensions, so 2 plus 1 plus so time plus two transverse dimensions. Two transverse dimensions are put on the lattice in links and so on. There's an adjoint representation scalar field, which is the A eta. And then you do use the Kogut-Susskind lattice Hamiltonian formalism, which has explicit electric fields and links. So it's a gauge invariant formulation for solving lattice Yang-Mills theory on a spatial lattice, somehow it's written down spatial lattice and continuum time. And of course, continuum time is okay because we're kind of already we also put a tau equals 0. That's the gauge choice. So kind of we are also not doing time dependent gauge transformations because that would break our gauge choice. So we can use we can have continuous time, but there is a two-dimensional lattice invariance still left, which is dealt with the proper lattice way. So that's the IP Glasma code is a time plus two transverse dimensional code, Kogut-Susskind Hamiltonian formulation for a Yang-Mills 2 plus 1 plus 2 2D two spatial dimension Yang-Mills theory with an adjoint scaling. Good. So now let's take the energies, and then you match the energies to hydrodynamics. We'll take a break first, and then we'll discuss a little bit what this. I'll then draw pictures of what these fields look like. But let's take a break first. Good. So these are now our initial conditions. So it's useful to think, let's say entertaining to think a little bit about what they mean. First of all, a curious thing about Yang-Mills theory is that you remember that these two were pure gauge fields, which means that if I take one of these fields and I calculate the energy density of the field, actually if I calculate F mu nu, the field strength tensor, the field strength tensor for either of these fields separately is 0, right? Kind of they are gauging. These are separately gauge equivalent to the vacuum. And if I was doing a billion theory, if I take two gauge fields that are gauge equivalent to the vacuum, the sum would be gauge equivalent to the vacuum. But that is not the case in a non-abelian theory, right? So the sum of two pure gauge fields is not a pure gauge field. Okay. There is a one non-zero component of the field strength tensor, which you can get from this, and that component is the Fij. So remember, my I and j are only transverse pieces, right? So this means that this is kind of an Fxy component, which is a z component of a magnetic field. Fx, it's Bi is epsilon I j k jk, and so if these are transverse components, epsilon ij tells me that this is a longitudinal magnetic field. Okay, and so how does one calculate? How does one calculate the field strength tensor from the gauge potential? The field strength tensor is, let me write this down. Ij is Di Aj minus Dj Ai. I'm not sure whether, depending on your, I'm not sure whether in my conventions there's a plus or a minus. And then I think in my conventions I needed G here. Aj. Very unsure about the sign of this, right? So if I plug this in here, you will see that of course I have the linear terms, which are just the sum. The linear, the differentials of the sum are the sums of the derivatives. That's somehow straightforward. Then in the quadratic term, I have of course the term where I get just the A1 commutator with itself, or commutator with the other component. Remember that the components I and j are different. So the x component of this does not commute with the y component. But the quadratic terms anyway, the quadratic terms cancel these derivative terms. The terms that only involve A1 just go away, because A1 has, this is a pure gauge field, it has 0 F mu nu. The same thing for the terms that only have A2, the field of nucleus 2. They give you 0 field strength. The only thing that remains is I, G, A, 1, I, and A, 2, J. So this is the magnetic field. So I have a non-zero. So this is BZ. The Z I have at the initial tau zero, I have a longitudinal magnetic field from this longitudinal magnetic field from these correlators. Then the other, sure, I can use it too. So I have a longitudinal magnetic field. Let's see. Then what else do I have? One could, of course, ask whether one could of course ask whether I have a transverse electric field. Will I have a transverse electric field F0I? If I go to eta equals 0, then that it is the easiest. Then somehow it is. Then I just get somehow Z component. So it's easiest to calculate that eta equals 0. Now F0I, which would be a transverse electric field, not obvious from this, but in fact, that would be the time derivative of these. It is not obvious, but that actually is going to be 0, basically because of the boost invariance. And I'm not going to. We can figure this out if you want. Maybe in the third session. I'd have to think a little bit about how to derive this, but nevertheless, the transverse electric field is 0. Then let's look at A eta. So A eta, maybe the easiest way to think is that again, if I go to eta equals 0, I need to think about dimensions. A eta now has somehow this has an energy dimension of energy, this has a dimension of energy. So it means that A eta is kind of has dimensions of just dimensionally, it's going to go like 1 over tau. Hope I'm getting this right. A z, which means that A z is going to go like tau A eta. So the way I'm just thinking about this is that I mean, because I'm too sloppy to actually do the proper calculation using the definition of this coordinates. Not just somehow guessing my way to the right answer because I know what the right answer is. But if I was doing this properly, I would write down all the transformations of how do you go from tau and eta coordinates, tau and eta components to other components. But now I'm just somehow trying to recall myself how to get the right answer. So A eta, so A eta is basically 1 over tau Az at eta equals 0 up to science, which means that Az is like tau A eta upstairs, which means that F0z, which is like a time derivative of Az, is non-zero. Taking a time derivative of Az gives this tau, and you get A eta. So F0, the F0z component at tau equals 0 is basically this A upper eta at tau equals 0, plus or minus. Okay. So this is non-zero. So what is F0z? This is a longitudinal electric field. So those are the components I have. Then what about Fzi? Well, Fzi, it's kind of there's two terms. You can have a longitudinal derivatives of transverse gauge potentials. But basically, again, if I go, it's easiest to somehow think at eta equals 0, and because all of my fields are boost invariant, they do not depend on z coordinate. So I don't have a z derivative of, at least at eta equals 0, I do not have a z derivative of the transverse gauge potential contributing to this. The other option would be to have a transverse derivative of the z component of the gauge field, but the z component of the gauge field goes like tau times something which is finite. So this also is 0 at tau equals 0. Okay. So this means that what do my plasma, Larry, I'm trying to reproduce the picture that Larry likes to draw. So here's my nucleus 1, which is, this is after the collision. Here's my nucleus 1. Here's my nucleus 2. So these are the nuclei that have already collided. They're going away from each other. They're receding. And we're interested in what is the stuff in between here. There are charges on these nuclei. These were the color charges now. Color charges now current, which we don't have anymore because we already eliminated using the equation of motion. So we had color charges, they went through each other. Associated with these color charges were, you remember, we had transverse E and E fields. So they kind of follow the sheet. These were the FI, the parts of the field strength that were having delta functions on the light cone, for delta x minus or delta x plus. They were transfers. These were like normal kind of a gluon cloud accompanying a charge. A gluon going in the z direction will have transverse E and B fields that are transverse to the z direction. But they live only here where the charges live on the light. What we have behind is in this dithrapid region, this is what is going to become our plasma, are color electric fields and color magnetic fields, which initially only have a longitudinal component. And this longitudinal fields, I think the statement that these are longitudinal fields has caused an enormous amount of confusion.
Just ask, it's interesting that we have E and B, so E dot B is non-zero.
Yeah, so this is one of that was actually somehow the main point in the paper where paper written by me and Larry, where Larry came up with the name Glasma, was that, oh, there's actually an E dot B, and maybe that could, and of course, so there is an E dot B. It's kind of fluctuates, so somehow there's not, on average, it kind of depends on, you have to go back to where do the Wilson lines come from, what are the charge distributions. Typically your if your row correlation, you can calculate this in the MB model. Your row correlation is color singlet, so it means that you can figure it out that expectation value of E dot B is 0, but E dot B squared expectation value is not 0. So you have event by event fluctuating Chern-Simons current, and that has led to its own kind of own field of people trying to, I mean, this is whether people trying to figure out whether how large these fluctuations are, how much do you have in the later stages, do you see signals, CP violating signals that fluctuate event by event. There's this whole chiral magnetic effect industry that is kind of trying to look at this kind of whether you actually see E dot B. I mean, whether you actually see signals that could somehow be related to this. So far, that is a really conclusive. So the fields are longitudinal. The fields are longitudinal at tau equals 0. That's the crucial, and that's the crucial point. The other thing is that Larry dedicated this paper to Drew Anderson, with whom he had apparently had long discussions about strings back in the day before my time. And so it is interesting that a longitudinal color electric field is the same thing that you have in the string model of hadronization. If you take two color charges, I mean, if you take Pythia string model, what you have is you have a hard scattering. You have partons that after the hard scattering, and the beam jets are receding, just like these charges. And in Pythia, in the Lund string model, you have a color electric field, and that's what produces all of the stuff that, all of the soft QCD stuff in there. All of the soft QCD stuff in Pythia, the event generator, comes from such an electric field, which then decays by some non-perturbative mechanism to particles. So there's I had interesting discussions with people from Lund trying to understand, okay, what exactly are the similarities and differences between this picture and the string fragmentation. And I'll try to explain you what I see as the biggest difference in terms of the physics, in terms of physics. So there's a longitudinal electric field, there's a longitudinal magnetic field. Initially at tau equals 0. Okay. In some sense, I think it is inevitable. Well, it's not inevitable that you have both. You could consistently have just one. But I think once you go through this, go through the coordinate transformations, I think it's basically boost invariance forbids you from having. If you have the assumption that fields are boost invariant, do not depend on space-time rapidity, you cannot really have transverse EMB fields. That they would require something blowing up like 1 over tau as at tau equals 0. So somehow these kind of are the only things that are consistent with boost invariance at the field configuration level. But the fact that whether they are both non-zero is a little bit more non-trivial statement. Okay, so then I had this discussion with Al Muller, who was telling me, I don't believe you. You cannot have longitudinal fields. And Al Muller is a grand old man of the QCD. And of course, when he says that you cannot have longitudinal fields, you take him seriously. But the point in for Al is that I quickly realized that it's a question of longitudinal with respect to what. When Al says that you cannot have longitudinal fields, what he thinks is that if you have a gluon going in some direction with some momentum in some direction, the electric and magnetic fields are transverse with respect to the direction of the gluon. Here, this is electric and magnetic field which are longitudinal with respect to the beam axis. But there's no contradiction because kind of these correspond to these classical fields. If you want to think of them as particles, which we should do, they correspond to gluons that have a momentum in the transverse direction. So you have a gluon with a purely transverse momentum, well, it's a purely transverse at eta equals 0 and then boost invariant in other frames. Okay. So come on, boosting to other frames in some other frame, it will have a Z component, but that's only given by the boost from something which is purely transverse with rapidity. So because the beam axis, that we perfectly will have a field which is longitudinal along the beam axis and makes transverse with respect to the momentum of the gluon. And in fact, this is what we should have, and this is the way one should think about this, because the other difference with respect to the Lund model is that now these color charges, they come from Wilson line, and they come from the Wilson lines. And you remember that the Wilson line correlator has this saturation scale. So there is a characteristic scale, and these color electric and color magnetic fields, they are all the color components separately. They are functions of the transverse coordinates. And there's a characteristic scale in this transverse coordinate dependence, which is 1 over the saturation scale, which means that these are, if I think of these classical fields as gluons, I'm really kind of emphasizing the particle wave duality here. I have gluon fields, I'm calculating as a gluon field, but I should simultaneously be thinking of these gluon fields as also being particles. I Fourier transform from coordinate to momentum, and I look at the momentum mode. This momentum mode I can interpret as a particle. So the fact that everything depends on transverse coordinate with a characteristic length scale 1 over qs, it means that these are gluons that have transverse momenta that are of the order of the saturation scale qs. Okay.
Sorry.
Yep.
I don't know if this is true in this classical Young modes, but I'm thinking in terms of like in electrodynamics, where usually the energy is transferred in terms of the direction like E cross speed. And I feel like if you've got these particles, they should be carrying some sort of energy with them. So it seems weird that that's E must be zero. Is that still true in the angles, or is that?
That depends a little bit on the polar. It's a question of the polarization state. And actually, that is very good question. Is coming to my kind of next delicate point about this. So, but let's start. Actually, that's a good one. Let's start from electrodynamics. And let's start from electrodynamics. And let us consider a linearly polarized photon. Okay, it's just classical E. So photon I'm not gonna do the usual kind of exponential time. I want to really be, these are classical fields, these are real numbers. I don't want them to be exponential ik dot x. I need them to be sines or cosines, right? So let's have the photon having a momentum in the z direction. Okay, has a z direction in the momentum. And I'm choosing a particular linear polarization state. Of course, you can choose you know that photons have two polarization states, and you can make linear combinations of these polarization states. So there are many options. I will choose an option that kind of an option that you don't usually see. I will say that my photon, which is a momentum in the z direction, has a electric field which has, so clearly it has a momentum in the z direction, so the pointing vector should be in the z direction. It's transporting energy in the z direction, right? I can, for example, say that it's the x component. It has an x component electric field, which is a sine of sinusoidal oscillation with the absolute value of kz t minus kz z, like this. And then I will have a magnetic field y component, and these are oscillating in time. So somehow Maxwell's equations are going to tell me that E fields and B fields are time derivatives of each other. So the B field is going to be a cosine of the same thing minus kz z, right? So I just now came up with this example on the fly. I hope you'll tell me if this is if you don't think this is a valid electric and magnetic field configuration for a photon, right? So it has kz. Certainly, it's transporting momentum in the z direction. But if I choose to look at it at t equals 0 and z equals 0, why not? It's a point in space-time. Well, if I look at it at t equals 0 and z equals 0, it will have an electric field that is purely 0, and it will have a magnetic field that is 1. So what's the pointing vector? Yeah. It should be, I mean, but nevertheless, this is a perfectly valid photon, which is, perfectly valid radiation quantum in the
example with gluons that were both non-zero, right?
No?
Weren't they both explicitly non-zero in the gluon case?
Well, okay, so now I choose my axis a little bit. Let's choose my axis in a different way. I make this x, and I'll make this y, and I'll make this z, right? And now I have a photon or a gluon, which has a momentum in the x direction. And if I look at it at a specific time, and now here I have the y equals, if I choose to look at it at a specific time, it's oscillation. it will have a zero electric, it's going to have an electric field transverse component, transverse to y component electric field, which just happens to be zero at this time. And it's going to have a non-zero z component magnetic field. So this is actually just like this. So if I want to think of these plasma fields as gluons, they are going to be gluons like this, and they're going to be gluons that have transverse momentum, which I can split into polarization states. So now the point is that there are two possible polarization states. I mean, if I could also have a kx. I could of course also have a by, which is a sine, and an ez, which is a cosine. So I have two independent polarization states. So for example, if I have a momentum in the x direction for my photon, I could choose my two polarization states to be these ones. And then of course I can put some phi, I can put some phase. This can be in some arbitrary phase, but in some cases I might have a physical configuration where this phase is zero, and this is kind of a choice of this phase is kind of a choice of what do I decide to call time equals zero. If the phase is equivalent to say that I can't find time starting from a different point. So that's not really important. So you can have these kind of two polarization modes. The other one has a magnetic field which is zero and a electric field which is non-zero. Ez is not zero at t equals zero. So here I have a configuration where at the zero time I have a longitudinal electric field and a longitudinal magnetic field. So this is perfectly consistent with this kind of a purely normal gauge bosons, non-interacting gauge boson. So this is why you can take this initial condition and you can do a further calculation, which is actually what Heribert and company did in their paper, where you're starting from this initial condition, you just say that, okay, I'm going to linearize the equations of motion. I'm going to treat these guys as photons, and these are the kind of photons they will be. Except there's the expanding coordinates involved a little bit, but essentially in terms of the most important aspects, they are like this. So the fact that photons or gluons with transverse momentum have two polarization states. You can choose the two polarization states to be, for example, these kind of such linearized polarization states. The fact that you have an electric and magnetic, chromoelectric and chromomagnetic field here means that these two polarizations you are producing two. So you are producing both of these polarizations, both of these kind of polarization states. So that you can think of the electric field as that's the initial condition for one particular polarization state. And then the longitudinal magnetic field is the initial condition for the other polarization states. And we are producing gluons in these two polarization states. What is the answer to Al's question is these are perfectly fine fields for a gluon that has a momentum in the transverse direction. The only non-trivial thing here is that something that kind of followed from the boost invariance. It kind of really follows from the boost invariance at the field configuration level that we start in this particular mode. I mean, these oscillate between these two, right? The sinus and cosine, they oscillate between the electric and magnetic fields. Both polarization states independently oscillate between the two. but now basically the boost invariance at the field configuration level dictated to us that at tau equals 0, we must start with the longitudinal fields. So this means that the boost invariance imposes on us a specific somehow coherence. It imposes on us the fact that this mode must, which is oscillating between these two things, must at tau equals 0 start with this one. And the other mode, which is oscillating between these two things, it just has to oscillate like this. So, so it is the boost invariance in some sense, which is imposing on us that we are producing modes where this phase phi 0 happens to be 0. And that's the only non-trivial thing. And sometimes people think of this as gluon, but there's the classical field calculation gives you a coherence for the fields at the initial time. And that is something that is very, if you just calculate Feynman diagrams like that is doing, if you just a lot of the physics you can get by just calculating this and squaring it, and you get some calculation for how many of these photons you are producing. But in this calculation, you're kind of only looking at asymptotic states, and whereas doing the calculation like this in terms of classical fields allows you to say something about time dependence. Okay. So now starting from this cartoon, of course, this was all tau equals 0. This was all tau equals 0. So then what happens later as a function of tau? What you can so let me just plot what you get by numerically solving the equation of d mu f mu is 0. So this is tau, and this is 0. So you start with the E and the B fields somewhere here. They're actually basically rotation invariance actually dictates that the expectation value of E squared and the expectation value of B squared is the same. Lattice, you don't exactly get this because you break rotation invariance. But anyway, so what happens is that the E fields then, so this is the B field, choose another color. So these are like how should I say, the expectation value of E Z squared. Expectation value taken like the M Maclaurin Berengopola MB model for the color charges, and then going through the whole calculation and getting this, and then this is the expectation value of the EZ squared. Okay. But then just like these polarization modes, so we have the typical momentum, the typical gradient, the typical transverse derivative of these modes is of the order of QS. And so this means that this typical frequency at which they oscillate is also QS. So this means that the typical time scale at which something starts to happen to these fields is also QS. So here there's a time scale 1 over QS. And then the other fields, like this, and like these are really on top of each other. So this would be now, be careful, the E x squared plus E y squared. And this would be bx squared plus by squared. Okay, so this is what happens when you solve the equations of motion numerically. at a time of 1/q of the order of 1/q, as well, there are different, there's a superposition of momentum modes, right, that have a little bit of different momentum, therefore they oscillate at a little bit of a different frequency. And when you go forward in time, at some point they get out of phase. So you lose the coherence. You start, all of them started at a very particular phase in their oscillation, but after some time of the order of QS, they lose the coherence. And then there's kind of everyone is just somehow in their own phase, and things average out. That happens at time order of QS, yes.
What's the line?
No.
Vertical axis, where does it end? It's the.
Well,
Where do they get?
dimensionally, this is a dimension. This is a dimension for observable. So this has to be some number times QS to the fourth. It's a one scale problem, and QS gives all the dimensions. And this number, then you have to work hard to calculate. Good. So this is what happens. Eventually, you have these. Eventually, you start oscillating between these two, and what you get, but not so. And these become approximately equal. So you now see that the other thing that you see in this late time. Yeah. So this kind of a behavior is perfectly consistent with kind of your image as in terms of the intuition you get from the photons, right? Now what you see is that so these become all these lines become approximately equal. So this means that from this you can see that the system is nevertheless not isotropic, and it kind of shouldn't be. It's not isotropic. It's not isotropic because at late times, so EZ squared is about the same as EZ squared, which is about the same as x squared plus y squared, which is about the same as bx squared plus by squared. This is what happens. So you, of course, if this was isotropic, the EZ would be of the same order of EX squared, but it's not. So the longitudinal fields remain on average twice as large as an individual component of the transverse field. What this you can turn into, and this is a this becomes understandable if you turn this into components of the energy momentum tensor. You can calculate the energy momentum tensor T mu nu, and there's a well-established expression for what is the energy momentum tensor of a gauge field. Just take different components of these in different combinations and write it in my notes. I'll not try to write it down here because I would get lost. And then what I will use the nomenclature of matching this, so you can calculate the energy momentum tensor, and I will just call the diagonal components of this energy momentum tensor E and minus, let's use it, Ex squared, Py squared, Pc minus Pz squared. So I can calculate the energy momentum tensor from my F mu nu. There's a well-established expression. It's a quadratic expression. It's easy. But the specific linear combinations of these. Typically, if you want to interpret the energy momentum tensor in terms of energy density and pressure in hydrodynamics, especially, or in general relativity, this is what you do in cosmology. You say that the 0,0 component of the energy momentum tensor is the energy density, and the other diagonal components are the pressures. So these are just now some specific linear combinations of these T squares and D squares. And what the energy momentum tensor then like if you use this time dependence, is that as a function of tau, here is your energy density. Oh, and this is a classical Yang-Mills field. So the energy density, energy momentum tensor is explicitly traceless. So which means that the sum of, so that the three pressure components sum up to the energy density. Things. Then you have the longitudinal pressure, the Z component pressure starts off being negative and minus the energy density. And then you have transverse components, which let me draw like this. This is 2 times px, which is the same as 2 times py. And again, of course, the characteristic time scale here is 1 over qs. But in terms of energy density, this is really clear. This is what happens. This is what happens if you have purely longitudinal electromagnetic fields in the same direction. Only if you want, and this is kind of, you can always calculate the energy momentum tensor. Whether you want to interpret it as a pressure or not depends on how you interpret it. But if you want to interpret it as a pressure, at tau equals 0, you have a negative pressure, which is equal to negative longitudinal pressure, which is equal to the energy density. But then at later times, I hope I'm getting this correctly. Yes. No, I am making something crazy. Actually, possible. I'll draw this in another way. Sorry. Actually, this is now x, which is approximately y. It's now your no, I'm still not doing this right because I'm looking at Francois' plot and this is normalized in that. Yes. So actually, sorry, it is the at tau equals 0. I have that Pz is minus energy density and Px and Py are equal to the energy density, which means that Px plus Py plus Pz is equal to the energy density. This is my energy momentum tensor is traceless. So the longitudinal pressure is negative. The transverse pressures are equal to the energy density. So this is very weird. Yes.
And would that not be squares in the momentum?
Oh, absolutely not. Yes, you are absolutely right. And that somehow getting lost between pressure and momentum. So pressure, energy density, pressure. This is at tau equals 0. So this is weird, but this is a reflection of the fact that I have this very coherent classical gauge configuration. It's very weird. How much greater than 1 over qs around here? This is also special, but not weird. More easily understandable. In this case, I will have Pz will be going to 0. It's very small, and then I have the energy density will go like 1 over tau, and the longitudinal and the transverse pressures will both be approximately energy density divided by 2. So there's two different things that one can see here. So this, first of all, the fact that the energy density goes like 1 over tau, this is a result of Booth invariance. One way to think about it is that we have a Booth invariant configuration, and remember I already erased this. We have a Booth invariant configuration, and these are equal rapidity lines, are straight lines like this. So it means that the energy per unit rapidity is constant, but because the one unit of rapidity becomes larger and larger, it means that the energy per unit z goes like 1 over time. So the energy per unit rapidity is constant, but one slice of rapidity is a bigger and bigger slice of z coordinate. So energy density goes down. Everything goes like 1 over tau as a consequence of Booth invariance. And this is very reasonable. This is what hydrodynamics, like this is what really happens in heavy ion collisions. This is a pretty good approximation. Well, pretty good, and then you can get to details, but a relatively good approximation. But then what you see is here is that the longitudinal pressure goes to 0 quite rapidly, and you only have transverse pressures. So this means that, and this is also a consequence of Booth invariance, it means that your system is very anisotropic. Because the Booth invariance really means that the Booth invariance, it means that nothing depends on eta. So the best way to think about it is that at eta equals 0, nothing depends on z. And if field configurations do not depend on z, it means that particles have no momentum component in the z direction. So particles do not have longitudinal momentum. They only have transverse momentum. This of the order of of the order of qs. So particles only have transverse momentum, not longitudinal momentum. The system is very anisotropic, and kind of then the question of thermalization in heavy ion collisions is how do you go from such an anisotropic system to a at least close to isotropic particle plasma, and that's what we are going to talk about tomorrow. But here I think this is a good point of finish. Okay. Questions?
Okay. There are no questions, then I'll stop the recording.